Hello, my name is Shaan Patel and I'm a fourth year PhD candidate in the Department of Physics. My advisor is Dr. Manfred Kuntz. Today I'll be presenting my work published in monthly notices titled Orbital Stability of Hierarchical 3 and 4 Body Systems with Inclination. As more possible exomoons are discovered, we are motivated to explore the orbital stability of these bodies through the use of n-body simulators such as Rebound. We focus on the system Kepler 1625 by first exploring the 3-body case including the star, planet, and potential moon. After finding stable regions for the moon, we expand this test into the 4-body case by adding a submoon to the hierarchy. Submoons, or moons of moons, have yet to be discovered, even in our own solar system. However, we believe they may exist as one more body in the star-planet-moon hierarchy. We also investigate the 3-body case of the Kepler 1708 and HD 23079 systems, while also investigating a 4-body case for HD 23079. Moving on to the methodology, we run a 2D parameter space of n-body rebound simulations exploring the exomoon's initial semi-major axis and inclination. The exomoon's parameters are taken from the literature for Kepler 1625 and 1708. These simulations are ran for 100,000 years with a stop put in place if the exomoon leaves the planet's hill radius, automatically marking the moon as unstable. Maximum eccentricity of the exomoon is tracked throughout the simulation as a proxy for stability. After analyzing the stability of the 3-body cases, we expand this to the 4-body case for Kepler 1625 and HD 23079 by adding a putative submoon. The parameter space is similarly built, and simulations are ran for the same length of 100,000 years. Figure 1 here shows the 4-body case for Kepler 1625 with the gray areas here representing the parameter space we explore for the submoon. We find interesting resonance curves that are explored using 3 numerical and analytical methods. Secular resonances occur when precession rates from multiple bodies overlap. This can lead to orbits changing shape and higher eccentricities, which increases instability rates. Firstly, we use raw time series data on the epsilon precession rates of the moon and submoon to find integer ratios that could possibly point to a secular resonance. We then use the built-in chaos indicator in Rebound known as MEGNO, which tests for chaotic orbits in the simulation. Finally, we use secular perturbation theory to run secular simulations to compare to our Rebound results. Moving on to results, I would like to start with the 3-body parameter spaces first. From left to right, we have Kepler 1625, HD 23079, and Kepler 1708. The logarithm of the maximum eccentricity is plotted here. Each pixel here represents 10 simulations averaged over the maximum eccentricity. The black lines represent parameters from the literature, while the white dots represent the parameters used for the 4-body case. Firstly, we see the unstable purple region starting around 45 degrees for all panels, which corresponds to the von Zeipel-Leydov-Kozai effect, or ZLK effect for short. This effect is well known in 3-body systems where the inclination and eccentricity of a body fluctuates. Given a high initial inclination, fluctuations to a higher eccentricity will occur, leading to the body becoming unstable over time. We also see a gradient along the x-axis where a larger semi-major axis of the moon leads to higher eccentricity due to more perturbations by the host star. In conclusion, we see that most of the parameters from the literature fall within the stable regions except for a few select high inclination cases. Moving on to the 4-body case, we see a similar result at higher inclinations due to the ZLK effect. More notably in the stable region is the resonance curves we see that lead to instabilities. Looking at the time series epsilon precession rate data, we find a potential 13:2 resonance between the moon and the submoon. From our MEGNO tests, we find that our 2 distinct curves appear in just 100 years, leading to another test strongly suggesting a secular resonance. This can be seen here in figure 4, where these curves here are matching these curves found in figure 3. Our last test is our secular perturbation theory test, which effectively simulates our system without the inclusion of non-secular effects, including mean motion resonances and short period perturbations. From these tests, we find that the fluctuation of submoon inclination matches the rebound case up to our frequency shift, which we can see here in figure 5. This is our third and final confirmation of a secular resonance. Our main conclusions are that the exomoon parameter estimates given in the literature are mostly situated in stable regions pointing to viable exomoons, with an exception for high initial inclinations which are expectedly unstable. We also find stable and unstable regions for the putative submoons, with secular resonance curves throughout the parameter space. Our work will act as a framework for future exomoon candidate explorations, along with investigations into the existence of submoons in the universe. I would like to thank my co-authors Dr. Billy Quarles and Dr. Manfred Kuntz for their hard work and guidance on this publication. Thank you for your time.